Let's look at small animated video to understand the topic that we are going to learn now.
Last summer, my family and I visited Russia. Even though none of us could read Russian, we did not have any trouble in figuring our way out, all thanks to Google's real-time translation of Russian boards into English. This is just one of the several applications of neural networks. Neural networks form the base of deep learning, a subfield of machine learning where the algorithms are inspired by the structure of the human brain. Neural networks take in data, train themselves to recognize the patterns in this data, and then predict the outputs for a new set of similar data. Let's understand how this is done. Let's construct a neural network that differentiates between a square, circle, and triangle. Neural networks are made up of layers of neurons. These neurons are the core processing units of the network. First, we have the input layer, which receives the input. The output layer predicts our final output. In between exist the hidden layers which perform most of the computations required by our network. Here's an image of a circle. This image is composed of 28 by 28 pixels, which make up for 784 pixels. Each pixel is fed as input to each neuron of the first layer. Neurons of one layer are connected to neurons of the next layer through channels. Each of these channels is assigned a numerical value known as weight. The inputs are multiplied to the corresponding weights, and their sum is sent as input to the neurons in the hidden layer. Each of these neurons is associated with a numerical value called the bias, which is then added to the input sum. This value is then passed through a threshold function called the activation function. The result of the activation function determines if the particular neuron will get activated or not. An activated neuron transmits data to the neurons of the next layer over the channels. In this manner, the data is propagated through the network. This is called forward propagation. In the output layer, the neuron with the highest value fires and determines the output. The values are basically a probability. For example, here, our neuron associated with square has the highest probability. Hence, that's the output predicted by the neural network. Of course, just by a look at it, we know our neural network has made a wrong prediction. But how does the network figure this out? Note that our network is yet to be trained. During this training process, along with the input, our network also has the output fed to it. The predicted output is compared against the actual output to realize the error in prediction. The magnitude of the error indicates how wrong we are, and the sign suggests if our predicted values are higher or lower than expected. The arrows here give an indication of the direction and magnitude of change to reduce the error. This information is then transferred backward through our network. This is known as backpropagation. Now, based on this information, the weights are adjusted. This cycle of forward propagation and backpropagation is iteratively performed with multiple inputs. This process continues until our weights are assigned such that the network can predict the shapes correctly in most of the cases. This brings our training process to an end. You might wonder how long this training process takes. Honestly, neural networks may take hours or even months to train. But time is a reasonable trade-off when compared to its scope.
To understand how an artificial neural network works, we need to understand how the real one works. First, we have a direct input to the neuron. And you can see these little hairs that come in and they receive information. Then we have the cell body information processing happens here. So it takes all these different dendrite information coming in from the different dendrites, and it looks at that information. And then you have your axon, which is the output to the neuron. So there goes your axon, and you see it goes all the way out. And at the very end it flanges out. Each one of those little flanges connects to the dendrite or the hairs on the next one. Now let's see what an artificial neural network looks like. So an artificial neural network, we have an input layer, so that could be an array of data. Each one of those white dots in the yellow bar would represent, say, a pixel in the picture. Then you have the lines of connected to the hidden layers, which are your weights, and they add all those up on the hidden layers. And each one of those dots come like a cell does something with all the inputs, and then it puts an output into the next hidden layer, and so on into the output layer. So information processing happens here, input to the neuron, output to the neurons, so you can see how they are similar. We have an input, which is a yellow bar coming in, and then you liken each of the hidden layers to being a neuron, and it passes it to the next one, and so on. And then you have an output to the next neuron or an output to the real world. A neural network is a system of hardware and/or software patterned after the operation of neurons in the human brain. Neural networks, also called artificial neural networks, is a way of achieving deep learning. How does artificial neural networks work? Let us find out. How does an artificial neural network work? Hey, Siri, what is the time now? It's 12:30 in the morning, thanks. Let's find out how she recognizes speech. Here is a neural network and the different layers on it. So we have our input layer, our hidden layers, and the output layer. This is the sentence that needs to be recognized by the network. What is the time? So when it comes in, each one comes in as a pattern of sound. So what is the time first? Let's consider the word what, and you have what. And you can see each one of those in the sound bar probably looks a little different than that, just a representation comes in as a different pattern. Now we will split the sound wave for the letter W into smaller segments. So we split off W and then we take W and we analyze just W. As the amplitude is varying in the sound wave for W, we collect the values at different intervals and form an array. So we have 0.5, 1.5, 1.7, 1.9, that might be the different amplitudes coming in. And we feed the array of amplitudes to the input layer. So each one of those goes into its own box on the input layer. Random weights are assigned to each interconnection between input and hidden layer. So remember those little lines I said, those are special weights. Now we're going to start by doing it randomly. We always start with random Z. We start with some kind of preset identical pattern, like we set them all to 3. Take forever to train it, and you're less likely to get a good result. Where random works really well in this, the weights are multiplied with the inputs and the bias is added to form the transfer function. So we make a sum of all the weights times the values. We take 0.5, which is your x coming in, and we're going to multiply that by W1, W2, W3, so on, and then we get to the next level. We're going to add those together, coming in what's coming in, so we add the weight times x, and there's always a bias added in. If you ever build your own neural network, don't forget to add the bias, and otherwise tends to not work quite as well. You need that extra layer in there to help it. Weights are assigned to the interconnection between the hidden layers. The output of the transfer function is fed as an input to the activation function. So the output from one hidden layer becomes the input to the next hidden layer. Acoustic model contains the statistical representation of each distinct sound that makes a word. And so we start building these acoustical models. And as these layers separate them out, they'll start learning what the different models are for the different letters. Lexicon contains the data for different pronunciations of every word. So we have a lexicon at the end. We end up with the ABCD identifies the different letters in there. Now, the term acoustic model and the term lexicon are specific to his domain, the domain of understanding speech. Certainly when we're doing photographs and other things, you'll have different labels on here, but the process is going to be the same. And finally, we get our output layer following the same process for every word letter. The neural network recognizes the sentence you said, what is the time, so identifies AWHT, and then identifies that that's one word, what is the time, and so on. Is 12:30. That way, Siri can look up the time and read it back to you. So let's look at the advantages of an artificial neural network. So gentlemen, could you tell me the advantages of an artificial neural network? It's amazing how many times I've been in that situation where I have to explain to the people making the decisions in the company. It's amazing how many times I've been in the space where I have to explain to the owner of the company what the artificial intelligence and the neural network actually do. What are the advantages of an artificial neural network and what it can do for them and how it works? So an artificial neural network outputs aren't limited entirely by inputs and results given to them initially by an expert system. This ability comes in handy for robotics and pattern recognition systems. Artificial neural networks have the potential for high fault tolerance. Artificial neural networks are capable of debugging or diagnosing a network on their own. Very common use these days is to go through the log files and sort them out. Thousands of log files. If you're working as an admin, nonlinear systems have the capability of finding shortcuts to reach computational expensive solutions. As we see this in banking, where by hand, they have an Excel spreadsheet, and then they start building codes around that Excel spreadsheet. And over 20 years, they might build a repertoire of all these functions, and the neural network comes up with the same answers done in days, weeks, or even a month for a huge bank. So now we've come far enough to understand how a neural network works. Let's go ahead and walk through this a nice graphical representation. They usually describe a neural network as having different layers. You'll see that we've identified a green layer, an orange layer and a red layer. The green layer is the input. So you have your data coming in, it picks up the input signals and passes them to the next layer. The next layer does all kinds of calculations and feature extraction. It's called the hidden layer. A lot of times there's more than one hidden layer. We're only showing one in this picture, but we'll show you how it looks like in more detail in a little bit. And then finally, we have an output layer. This layer delivers the final result. So the only two things we see is the input layer and the output layer. Now let's make use of this neural network and see how it works. Wonder how traffic cameras identify vehicles' registration plate on the road to detect speeding vehicles and those breaking the law. That got me going through a red light the other day. Well, last month. That's like the horrible thing. They send you this picture of you and all your information cause they pulled it up off of your license plate and your picture nation gone through the red light. So here we are, we have an image of a car, and you can see the license plates on there. So let's consider the image of this vehicle and find out what's on the number plate. The picture itself is 28 by 28 pixels. And the image is fed as an input to identify the registration plate. Each neuron has a number called activation that represents the grayscale value of the corresponding pixel range. And we range it from 0 to 1 for a white pixel and 0 for a black pixel. And you can see down here we have an example where one of the pixels is registered as like 0.82, meaning it's probably pretty dark. Each neuron is lit up when its activation is close to 1. So as we get closer to black on white, we can really start seeing the details in there. And you can see again, the pixel shows us 1 up to there, it's like part of the car, and so it lights up. So pixels in the form of arrays are fed to the input layer. And so we see here the pixels of a car image fed as an input. And you're gonna see that the input layer, which is green, is 1 dimension, while our image is 2 dimension. Now when we look at our setup that we're programming in, Python has a cool feature that automatically does the work for us. If you're working with an older neural network pattern package, you then convert each one of those rows. So it's all one array, so you'd have like row 1, and then just tack row 2 onto the end. You can almost see the image directly into some of those neural networks. The key is though, is that if you're using a 28 by 28, and you get a picture, this 30 by 30, shrink the 30 by 30, down to fit the 28 by 28. So you can't increase the number of input in this case, green dots. It's very important to remember when you work on neural networks, and let's name the inputs, x1, x2, x3 respectively. So each one of those represents one of the pixels coming in and the input layer passes it to the hidden layer. And you can see here we have 2 hidden layers in this image in the orange, and each one of those pixels connects to each one of those hidden layers. And the interconnections are assigned weights at random. So that gets these random weights that come through that if x1 lights up, then it's going to be x1 times this weight going into the hidden layer, and we sum those weights. The weights are multiplied with the input signal and the bias is added to all of them. So as you can see here, we have x1 comes in, and it actually goes to all the different hidden layer nodes, or in this case, whatever you want to call them. Network set up the orange dots, and so you take the value of x1, you multiply it by the weight for the next hidden layer, so x1 goes to hidden layer 1, x1 goes to hidden layer 2, x1 goes hidden layer 1. node 2, hidden layer 1, node 3 and so on in the BIOS. A lot of times they just put the BIOS in as like another green dot or another orange dot and they give the BIOS a value 1 and then all the weights go in from the BIOS into the next node. So the BIOS can change. We always just remember that you need to have that BIOS in there. There's things that can be done with it. Generally most packages out there control that for you. So you don't have to worry about figuring out what the BIOS is. But if you ever dive deep into neural networks, you got to remember there's a BIOS or that answer won't come out correctly. The weight is some of the input is fed as an input to the activation function to decide which nodes to fire. And for feature extraction as a signal flows within the hidden layers, the weighted sum of inputs is calculated and is fed to the activation function in each layer to decide which nodes to fire. So here's our feature extraction of the number plate. And you can see these are still hidden nodes in the middle. This becomes important. We're going to take a little detour here and look at the activation function. So we're going to dive just a little bit into the math, so you can start to understand where some of the games go on when you're playing with neural networks in your programming. So let's look at the different activation functions. Before we move ahead, here's our friendly red tag shopping robot. And so 1 is a sigmoid function. And the sigmoid function, which is 1 over 1 plus e to the minus x, takes the x value. And you can see where it generates almost a 0 and almost a 1 with a very small area in the middle where it crosses over. And we can use that value to feed into another function. So if it's really uncertain, it might have a 0.1 or 0.2 or 0.3, or for the most part, it's going to be really close to 1 and really close to his case, to 1, the threshold function. So if you don't want to worry about the uncertainty in the middle, you just say if x is greater than or equal to 0, if not, then x is 0. So it's either 0 or 1, really straightforward. There's no in-between in the middle, and then you have the width to call the ReLU function. And you can see here where it puts out the value, but then it says, well, if it's over 1 is going to be 1. And if it's less than 0, so kind of just dead ends, and on those two ends, but allows all the values in the middle. And again, this like the sigmoid function allows that information to go to the next level. So it might be important to know if it's a 0.1 or a minus 0.1, the next hidden layer might pick that up and say, this piece of information is uncertain, or this value has a very low certainty to it, and then the hyperbolic tangent function, and you can see here, it's a 1 minus e to the minus 2x over 1 plus e to the minus 2x. And it's very much along the same theme, a little bit different in here, and that it goes between minus 1 and 1. So you'll see some of those goes 0 to 1, but this one goes minus 1 to 1. And if it's less than 0, it's it doesn't fire, and if it's over 0, it fires, and it also still puts out a value. So you still have a value that you can get off of that, just like you can with the sigmoid function and the ReLU function, very similar in use, and I believe the originally used to be everything was done in the sigmoid function. That was the most commonly used, and now they just kind of use more the ReLU function. The reason is wanted process is faster, because you already have the value and you don't have to add another compute the 1 over 1 plus e to the minus x for each hidden node. And the data coming off works pretty good, as far as putting it into the next level. If you want to know just how close it is to 0, how close is it not to functioning, is it minus 0.1, minus 0.2, usually they're float values, you get like minus 0.138 or something. So important information. But the ReLU is most commonly used these days as far as the setup we're using. But you'll also see the sigmoid function very commonly used also. Now that you know what an activation function is, let's get back to the neural network. So finally, the model would predict the outcome of applying a suitable activation function to the output layer. So we go in here, we look at this, we have the optical character recognition. OCR is used on the images to convert it into a text in order to identify what's written on the plate. And as it comes out, you'll see the red node, and the red node might actually represent just the letter A. So there's usually a lot of outputs when you're doing text identification. We're not going to show that on here. But you might have it even in the order might be what order the license plate's in. So you might have uptick, the alphabet plus the numbers, and you might have the 1 2 3 4 5 6 7 8 9 1 0 places. So it's a very large array that comes out as not a small amount of that we show 3 dots coming in 8 hidden layer nodes, 2 sets of 4. We just saw 1 read coming out a lot of times. This is 28 times 28. If you did 30 times 30, that's 900 nodes. So 28 is a little bit less than that, just on the input. And so you can imagine the hidden layer is just as big, each hidden layer is just as big if not bigger than the output is going to be. There's so many digits, it's a lot. It's a huge amount of input and output. But we're only showing you just it would be hard to show in one picture. And so it comes up and this is what it finally gets out on the output is identifies a number on the plate. And in this case, we have 08-D-03858 error in the output is back propagated through the network and weights are adjusted to minimize the error rate. This is calculated by a cost function when we're training our data. This is what's used. And we'll look at that in the code. We do the data training so we have stuff we know the answer to and then we put the information through and it says yes, that was correct or no because remember, we randomly set all the weights to begin with and if it's wrong, we take that error, how far off are you off, but as if it was like -1, you're just a little bit, if it's like -300 was your output. Remember when we're looking at those different options, hyperbolic or whatever, and we're looking at the RTL, the RTL doesn't have a limit on top or bottom, it actually just generates a number. So if it's way off, you have to adjust those weights a lot. But if it's pretty close, you might adjust relates just a little bit, and you keep adjusting the weights until they fit all the different training models you put in. So you might have 500 training models, and those weights will adjust using the back propagation. It sends the error backward, the output is compared with the original result. And multiple iterations are done to get the maximum accuracy. So not only does it look at each one, but it goes through it and just keeps cycling through these data making small changes in the network until it gets the right answers. So we talked about the neural network. This is a simple neural network, which must be trained to recognize handwritten alphabets A, B and C. And you can see here we have our input coming in. In this case, we'll look at the letter A written out on a 28 by 28 pixels. So the handwritten alphabets are presented as images of 28 by 28 pixels. And that image comes in this case, we have 784 neurons, that's 28 times 28. And the initial prediction is made using random weights assigned to each channel. And so we have our forward propagation as you see here. So each node is and their values are added up and so on going across. And our network predicts the input to be with the probability of 0.5, the predicted probabilities are compared against the actual probabilities, and the error is calculated. So the error is simply the actual minus predicted. And you can see here where we know it's not C, so it's a -2. We know is not B, so it's a -0.5, but we do know that it is A, so we go ahead and just set by 0.6. The magnitude indicates the amount of change while the sign indicates an increase or decrease in the weights. The information is transmitted back through the network. So here comes our back propagation weights throughout the network are adjusted in order to reduce the loss in prediction. So if we look at this setup, right here comes our error. In this case, 0.6 minus 0.5 minus 0.2 that comes up and adjusts our 1.4. 0.9 all are multipliers. In this manner, we keep training the network with multiple inputs until it is able to predict with a high accuracy. And you can see here we have a different that quickly switches from cursive to maybe more elongated. Similarly, our network is trained with the images for B and C too. So let's take a look at this. Here's a straightforward data set. Let's build a neural network to predict the outputs given the inputs. And so we have an input 0, we expect an output of 0, we have an input of 1, we expect 6, 2 equals 12, 3 should come out as 18, and 4 as 24. And we're just doing multiples of 6 if you're taking the time to look at it. So in our example, we have our input, and it goes into our neural network. So this box represents our neural network. One of the cool things about neural networks is they're always this little black box that you kind of train to do what you want. And you really don't have to know exactly what the weights are, although there are some very high-end setups to start looking at those weights and how they work and what they do. And then you get your output, which is going to be, in this case, our input's going to be X and our output's going to be Y, and W is the weight, so we have value times a weight. So if we're doing, in this case, just a single neuron going through, we have X times W. The network starts training itself by choosing a random value for W. We're going to guess that W equals 3, just roll the dice, randomly generate the number 3 for W, and then we put W equals 3, and here we have our input 0 or output 0, W equals 3 equals 0, so we have no error on the first line, that actually comes out correct. And then we have 1 times, we put the 1 in, we're looking for a 6. But we get a 3 instead. And we put the 2 and we're looking for a 12, we get the 6 and set. So you can see here, our predicted output doesn't match the output we're looking for. And then we take this, we have our W equals 3, and we come up with the second model where the W equals 6. Now we're going to look at how we figure out W equals 6 in just a minute. That is part of the math behind this, which you can see here. We put in W equals 6. And we build a W equals 6 chart. We end up with 0612 1824, which is the output we're looking for. And in that manner, we end up with the correct answer, but we'll go ahead and put in a third model where W equals 9. So at this point, this is one way of doing this, is just to guess what W equals, and you can see what W equals 9. We get the incorrect answers, we get 9182736. We as humans can know just by taking a look at the data that our weight should be 6. But how does the machine come to this conclusion? How do we program the computer to learn instead of waiting for us to tell it has the right answer what the correct answer is? And you can imagine this is a very simple problem. If we're doing guessing W equals 3, we guess W equals 6, we guess W equals 9. And then we look at our results, we go, oh, it's got to be W equals 6. That's the best result. But as humans, we want to take that element out and have the computer do that for us. So with that, we're going to have a loss function. The loss function is a measure of error, which defines the precision loss to comparing the predicted output to the actual output, and is simply loss equals actual output minus predicted output, and then we square the whole thing. So let's apply the loss function to the input value to loss for our actual output, predicted output squared, and our loss function for the input to 2 minute with an actual output of 12. And you can see here with W equals 312 minus 6 squared equals 36. So we end up with a loss of 36. W equals 612. 12 times 12 squared equals 12 minus 12 squared equals 0, or 12 minus 18 squared equals 36. And so you can see we have a huge loss on W equals 3 and W equals 9. We now plot a graph for the weight versus loss. And it always helps to have a nice visual of what's going on here. So this graphical method of finding the minimal of a function is called gradient descent. And this is the logic behind this. You can see as we come in here, we go ahead and graph the laws. We have 3643 and 3649, we happen to get 6, which was the correct answer right in the middle, and you can see right here forms a nice little parabola. And you can see a nice mark right in the middle. And as a human being, we can look at that, we go up. The answer is 6, a random point on this curve is chosen, and the slope at this point is calculated. So now we're getting away from the human aspect of just looking at it and saying what the answer is, and we look at what's going on with the math. And so if you have a positive slope, it indicates an increase in the weight, and a negative slope indicates a decrease in weight. This time the slope is negative. Hence, another random point towards its left is chosen. And you can see here, we're actually kind of just playing a little Halo game going back and forth with a gradient descent. We continue checking slopes at various points in this manner. So we have our input actual output, W3, W6, W9. We found our positive slope increase and increase in weight. A negative slope indicates a decrease in weight. A zero slope indicates the appropriate weight. So our aim is to reach a point where the slope is zero. And when we talk about neural networks, you're usually processing a massive amount of information and data. So you're not going to have all your data nice and neat, where it's just a multiple of 6, it's going to be messy. And so we're going to keep approaching that number, but you'll never get everything to fit at 0, you're going to get stuff all over the place. And so you're really looking for the minimum value, you're not looking for an absolute 0, cause you're not going to get it. We're talking about gradient descent, that's what we're talking about on there, is finding the bottom of that curve, even if it doesn't go all the way to 0. So how do we apply that to our neural network? Well, we use backpropagation. Backpropagation is a process of updating weights of the network in order to reduce the error in prediction. And so the magnitude of loss of any point on our graph combined with the slope is fed back to the network. And you can see here, here's our simple model with just one node of x times w. The input comes in, we have our x times w the output, and then we're going to propagate that loss going the other way. A random point on the graph gives a loss value of 36 with the positive slope, and we continue checking slopes at various points in this manner. So a random point in the graph gives a loss value of 36 with the positive slope. 36 is quite a large number. This means our current weight needs to change by a large number. A positive slope indicates that the change of the weight must be positive. Similarly, another random point on the graph is a loss value of 10. With the negative slope, 10 is a small number. Hence, the weight requires to be tuned quite less, and latest load indicates that the weight needs to be reduced rather than increased after multiple iterations of backpropagation. Our weights are assigned the appropriate value. You can see here we have our input. We just looked at x times 6 and our output, and eventually we get that the weight is 6 for the single node problem that we're working on right now. At this point, our network is trained and can be used to make predictions. Let's now get back to our first example and see where the backpropagation and gradient descent fall into place. And you can see here we're not looking at a single node anymore. Now we have 28 by 28 grid, or 784 inputs coming into the first level, which has 784 nodes, depending on how you build your neural network. The next layer might also have 784 nodes, or I might continually small and depending on what you need, and what's needed for that to work. So as mentioned earlier, our predicted output is compared against the actual output. And you can see our error over here, actual minus prediction. And then we go ahead and compute our loss. So the loss of is 0.7 squared equals 0.49, loss of BS, 0.5 squared or 0.25, and so on. So now we have our first iteration on there, so weights throughout the network are adjusted in order to reduce the loss in prediction. Now, of course, we do that by doing a second iteration coming through with or different losses on there. And then we throughout the network are just in order to reduce the loss of prediction again underneath the second, and we do a third iteration. And we just keep doing these iterations going back until we get the right value. Now you got to remember that when we're doing a reverse propagation, we're not looking at just one letter A, we're looking at hundreds of letter A's, and usually we propagate that loss going backwards, we only take a small piece of it. So our adjustments are very small. Because one of them is not correct, we don't want to create a bias. So we talk about backpropagation, we're talking about going through over and over this data until we get minimal loss for our letter A. So let's focus on the minimal loss for our variable A. And you can see here we look at that we'll assume for below to be our graph for the loss of prediction with the variable A as compared to the weights, continuing it from the second layer. And we have our loss of a 449, 416, 4.04. And you can see it makes this nice curve where we can guess where the bottom of this curve is. And I like it on this graph that they show that the curve doesn't rest on the x-axis, it doesn't rest at where y equals 0, because you usually don't get that. You don't get a perfect fit on anything, or very rarely to get a perfect fit. And so the random points shows on the graph is now back propagated through the network in order to adjust the weights. So we're able to go back through the network and readjust those weights until we find that minimal value. The network is run once again, with the new weights. This process is repeated multiple times to provide accurate predictions. The weights are further adjusted to identify B and C2, and this is interesting, because you actually do them at the same time. So, as the error goes back, you kind of find the overall error for all the inputs coming in. And then that's what gets propagated going back, or the overall loss. Kind of have to step away from that word error. Because it's not just about the error, it's about the loss. The weights are further adjusted to identify B and C2, and so a lot of times you actually do them all at the same time. But you'll adjust those weights, say, B and C, as I was just saying. Thus, through gradient descent and back propagation, our network is completely trained. And we've taught it to identify A, B and C coming forward. One of the interesting things about neural networks is the training process takes a lot longer than the predicting process. So you can plan one of these training neural networks during the back propagation to significantly longer, because you're going over 1,000s of data points. And then when you actually run it forward, it's very quick, which makes these things very useful. And just really part of today's world in computing. Today, we're going to be covering the convolutional neural network tutorial. Do you know how deep learning recognizes the objects in an image? And really, this particular neural network is how image recognition works is very central, one of the biggest building blocks for image recognition. It does it using convolution neural network. And we have the basic picture of a hummingbird, pixels of an image fed as input, your input layer coming in. So it takes that graphic and puts it into the input layer. You have all your hidden layers. And then you have your output layer, and your output layer. One of those I'm going to light up and say, oh, it's a bird. We're going to go into depth. We're going to actually go back and forth on this a number of times today. So if you're not catching all the image, don't worry, we're going to get into the details. So we have our input layer accepts the pixels of the image as input in the form of arrays. And you can see up here where they've actually labeled each block of the bird in different arrays. So we'll dive into deep as to how that looks like and how those matrices are set up. Your hidden layer carry out feature extraction by performing certain calculations and manipulation. So this is the part that kind of reorganizes that picture multiple ways until we get some data that's easy to read for the neural network. This layer uses a matrix filter and performs convolution operation to detect patterns in the image. And if you remember that convolution means to coil or to twist. So we're going to twist the data around and alter it and use that operation to detect a new pattern. There are multiple hidden layers like convolution layer. ReLU is how that is pronounced when that's the rectified linear unit that has to do with the activation function that's used. Pooling layer also uses multiple filters to detect edges, corners, eyes, feathers, beak, etc. And just like the term says, pooling is pulling information together. It will look into that a lot closer here. So if it's a little confusing, now we'll dig in deep and try to get squared away with that. And then finally, there is a fully connected layer that identifies the object in the image. So we have these different layers coming through in the hidden layers, and they come into the final area, and that's where we have the one node or one neural network entity that lights up. This says it's a bird. What's in it for you? We're going to cover an introduction to the CNN, what is conv neural network, how CNN recognizes images. We're gonna dig deeper into that and really look at the individual layers in the convolutional neural network. And finally, we do a use case implementation using the CNN. We'll begin our introduction to the CNN binary seems. A pioneer of convolutional neural network, Yanlo Kuhn. He was the director of Facebook. Our research group built the first convolutional neural network called LeNet in 1988. So these have been around for a while and have had a chance to mature over the years. It was used for character recognition tasks like reading zip code, digits, magic processing mail and automating that process. CNN is a feed-forward neural network that is generally used to analyze visual images by producing data with the grid-like topology. A CNN is also known as a convent net. And very key to this is we are looking at images. That was what this was designed for. And you'll see the different layers. As we dig in mirror, some of them are actually no use, since we are using TensorFlow and Keras or code. Later on, you'll see that some of those layers appear in a lot of your other neural network frameworks. But in this case, this is very central to processing images and doing so in a variety that captures multiple images, and really drills down into their different features. In this example, here you see flowers to two varieties, orchid and a rose. I think the orchid is much more dainty and beautiful. And the rose smells quite beautiful. I have a couple of rose bushes in my yard. They go to the input layer. That data is sent to all the different nodes in the next layer. One of the hidden layers based on its different weights and its setup. It then comes out and gives those a new value. Those values then are multiplied by their weights and go to the next hidden layer and so on. And then you have the output layer and one of those nodes comes out and says it's an orchid and the other one comes out and says it's rose depending on how well it was trained. What separates the CNN or the convolutional neural network from other neural networks is a convolutional operation forms the basis of any convolutional neural network. In a CNN every image is represented in the form of arrays of pixel values. So here we have a real image of the digit 8, that then gets put onto its pixel values represented in the form of an array. In this case, you have a two-dimensional array, and then you can see in the final inform, we transform the digit 8 into its representational form of pixels have zeros and 1 or the ones represent in this case, the black part of the 8 and the zeros represent the white background. To understand the convolution neural network or how that convolution operation works, we're going to take a sidestep and look at matrices. In this case, we're going to simplify it. We're going to take two matrices A and B, have one dimension. Now kind of separate this from your thinking, as we learn that you want to focus just on the matrix aspect of this. And they will bring that back together and see what that looks like when we put the pieces for the convolutional operation. Here, we've set up two arrays. We have in this case a single dimension matrix, and we have A equals 537,597. And we have B equals 123. So in the convolution, as it comes in, there's gonna look at these two, and we're gonna start by doing multiplying it times B. So we multiply the arrays element-wise, and we get 566, where 5 is the 5 times 1, 6 is 3 times 2, and then the other 6 is 2 times 3. And since the two arrays aren't the same size, they're not the same setup, we're going to just truncate the first one, and we're gonna look at the second array, multiply, just play the first 3 elements of the first array. Now that one's gonna be a little confusing. Remember, a computer gets to repeat these processes hundreds of times, so we're not going to just forget those other numbers. Later on, we'll see we'll bring those back in. And then we have the sum of the product, in this case, 5 plus 6 equals 17. So in our A times B our very first digit in that matrix of A times B is 17. And if you remember I said, we're not going to forget the other digits. So we now have 3 to 5, we move one set over, and we take 3 to 5, and we multiply that times B. And you'll see that 3 times 1 is 3, 2 times 2 is 4, and so on, we sum it up. So now we have the second digit of our A times B product in the matrix. And we continue on with that same thing, so on and so on. So then we would go from 37,527,592,597, this short matrix that we have for A. We've now covered all the different entities in A that match 3 different levels of B. Now, in a little bit, we're going to cover where we use this math that this multiplying a matrix is and how that works. But it's important to understand that we're going through the matrix and multiplying the different parts to it to match the smaller matrix with the larger matrix. I know a lot of people get lost at what's going on here with these matrices. Ooh, scary math. Not really that scary when you break it down. We're looking at a section of A and we're comparing it to B. So when you break that down in your mind like that, you realize, okay, so I'm just taking these two matrices and comparing them, and I'm bringing the value down into one matrix A times B. We're using that information in a way that will help the computer see different aspects. Let's go ahead and flip over again back to our images. And here we are back to our images. Time I go into the most basic two-dimensional image, you can get to consider the following two images: the image for the symbol, backslash. When you press the backslash, the above image is processed. And you can see therefore the image for the forward slash is the opposite. So we click the forward slash button. That flips very basic. We have 4 pixels going in. Can't get any more basic than that. Here, we have a little bit more complicated picture. We take a real image of a smiley face, then we represent that in this form of black and white pixels. So if this was an image in the computer, it's black and white. And like we saw before, we convert this into the zeros and ones, so the other one would have just been a matrix of just 4 dots. Now we have a significantly larger image coming in. Don't worry. We're going to bring this all together here in just a little bit layers. In convolutional neural network, we're looking at this, we have our convolution layer. And that really is the central aspect of processing images and the convolutional neural network. That's why we have it, and then that's going to be feeding in, and you have your rescue layer, which, as we talked about the rectified linear unit, we'll talk about that a little bit later. The revenue isn't how it acts, is how that layer's activated is the math behind it, what makes the neurons fire. You'll see that in a lot of other neural networks, when you're using it just by itself is for processing smaller amounts of data. We use the atom activation feature for large data coming in. Now, because we're processing small amounts of data, and each image, the ReLU layer works great. You have your pooling layer. That's where you're pulling the data together. Pooling as a neural network term is very commonly used. I like to use a term reduce. So if you're coming from the map and reduce side, you'll see that we're mapping all this data through all these networks, and then we're going to reduce it. We're going to pull it together. And then finally, we have the fully connected layer. That's where our output's going to come out. So we started to look at matrices. We've started looking at the convolutional layer and where it fits in and everything. We've taken a look at images. So we're going to focus more on the convolution layer. Since this is a convolutional neural network, a convolution layer has a number of filters and perform convolution operation. Every image is considered as a matrix of pixel values. Consider the following 5 by 5 image whose pixel values are only 0 and 1. Now obviously, when we're dealing with color, there's all kinds of things that come in on color processing, but we want to keep it simple and just keep it black and white. And so we have our image pixels. So we're sliding the filter matrix over the image and computing the dot product to detect the patterns. It right here. You're going to ask, where does this filter come from? This is a bit confusing, because the filter is going to be derived. Later on, we build the filters when we program or train our model. So you don't need to worry what the filter actually is. But you do need to understand how a convolution layer works. Is what is the filter doing? Filter, and you'll have many filters. You don't have just one filter. You'll have lots of filters that are going to look for different aspects. And so the filter might be looking for just edges and might be looking for different parts. We'll cover that a little bit more detail in a minute. Right now we're just focusing on how the filter works as a matrix. Remember earlier, we talked about multiplying matrices together, and here we have our two-dimensional matrix. And you can see we take the filter and we multiply it in the upper left image. And you can see right here, 1 times 1, 1 times 0, 1 times 1, we multiply those all together, then sum them, and we end up with the convolved feature of 4. We're going to take that and sliding the filter matrix over the image and computing the dot product to detect patterns. So we're just gonna slide this over. We're gonna predict the first one and just slide it over 1 notch, predict the second one, and so on all the way through until we have a new matrix. And this matrix, which is the same size as a filter, has reduced the image and whatever filter whenever that's filtering out.
Facial recognition. Cameras on smartphones these days can estimate the age of the person based on their facial features. This is neural networks at play, first differentiating the face from the background and then correlating the lines and spots on your face to a possible age. Forecasting. Neural networks are trained to understand the patterns and detect the possibility of rainfall or a rise in stock prices with high accuracy. Music composition. Neural networks can even learn patterns in music and train itself enough to compose a fresh tune.